Welcome to the Night's Open Circuit, the IEEE UCF official podcast. I'm your host, Antonia Jimenez.
And I'm Julia Lampert. In today's episode, we have Dr. Yuksel, and he's a professor in the ECE department. So can you tell us a little bit about yourself and where you're from and what brought you to UCF?
Sure. Well, first of all, thanks for having me. I came originally from Turkey. I was grown from there. And I came to the United States for master's and PhD in 1998. I did my master's and PhD in computer science at RPI, Rensselaer Polytechnic Institute, which is known to be the oldest polytechnic institute in the United States, known for their big projects and doing the Brooklyn Bridge and Pan American project in Sierra Nevadas. After that, I continued as a postdoc. I always had a passion for teaching in academia, found a faculty position in Nevada, Reno. Worked there for about 10 years. During that time, 1 year I worked in a company during my sabbatical as a software engineer. And returned back to academia and finally came to UCF. We wanted to have a change for the family as well as for myself, and joined the ECE department here. I also have joint appointment at Computer Science and CREOL.
Oh, that's great. We love the ECE department here.
Sure.
So, why did you choose your research in networking and wireless system lab? And can you share us more about your projects?
Sure. When I started my PhD, obviously a big issue was choosing a research topic. When choosing a research topic, it's crucial to find an area that is demanded. In academic system in the United States, thankfully, in some sense, we have a system that is incentivizing topics that are demanded out there. At that time, internet was booming. This is late 90s, and it was the time when everybody was getting online, and the companies and the businesses were establishing their websites. So working on something related to internet was very natural, and I found a research assistant position in a project that was funded by NSF, National Science Foundation, and that was it for me. We started working on networking issues. Specifically, there was the issue of congestion on the internet at the time, and coming up with methods to solve the congestion issue was very hot topic, very demanded. So I started there. But now when I'm looking at what happened over the years, again, based on what happened in the market and what is demanded, I ended up changing my topics. Of course, once you do PhD, you can't really change a lot. But by the time I finished my PhD, as a matter of fact, my PhD topic was obsolete. The reason being, there was a major revelation in the community, in the research community, that actually congestion was not really that much on the internet anymore. By the time I finished, it was like 2002. In late 90s, there was a lot of congestion. In just about 3-4 years, which is right about the time for a PhD, there was no more congestion left. So I was trying to price congestion on the internet for my PhD thesis, but there was nothing to price, if you will. So after my PhD, I ended up changing my topics, my research topics, depending on, again, what is demanded, what is needed, what relevant problems are out there. So currently what I work on are mostly on wireless systems. I try to solve problems related to capacity crunch on the wireless. In a nutshell, there's demand for more wireless data is literally exponentially increasing. It's a common phrase that a lot of the times people use, but it is exponentially increasing every year. There's more and more data being sent through the wireless ways. So I currently work on mostly on wireless systems, specifically optical wireless. I also continue my PhD topics, which was network economics in general. And but I use some of that knowledge for solving, again, issues related to spectrum management, radio spectrum management, which is a natural resource we all use when we are making communications using our wireless systems. So I use I use network economics to come up with better spectrum management policies in some of my projects as well. So
That's great. Sounds very interesting.
You talked about CREOL and optics a little bit. So do you mind telling us a little bit about free space optics and what it is and what you do with it?
sure, I'm happy to do so. As a matter of fact, you're right on the point that my affiliation with CREOL is mostly because of the research I'm doing in free space optical or optical wireless communication and networks. In a nutshell, if you want to describe it quickly, free space optics or free space optical communication specifically means that fiber optic communication without the fiber. We send data through fiber by essentially modulating the light beams, pretty much like flickering it, turning it on and off very fast. Our eyes won't be able to recognize it. And we do that right now in the fiber communications. But in free space optics, what we have is there's no guided media like fiber. And the transmitters, like lasers or LEDs, essentially keep doing this flickering. And on the receive side, we use photodiodes or photodetectors, excuse me, to capture that flicker and interpret that as data. Ones and zeros eventually. Essentially, that's what overall what it is. Why this is relevant right now is because optical bands, the visible light as well as the invisible infrared light, they have a lot of bandwidth. So these bands, in comparison to the traditional radio waves, which happen under 6 gigahertz. So pretty much all the cellular systems, Wi-Fi systems that we use today, they use radio waves that have frequency below 6 gigahertz. When you increase this frequency, what happens is that you have larger bandwidth available to you, but there are some physical aspects that you have to worry about and work with. The signal becomes more vulnerable to movements. The signal becomes more vulnerable to particles in the environment, in the air or other places, which means that it attenuates faster as it travels. So just to give a comparison, the wavelength of a radio wave typical today is in the order of tens of centimeters or sometimes even meters. The wavelength of an optical signal, is in the order of nanometers. So this means that if the signal is trying to penetrate through an obstacle that has thickness larger than its wavelength, which is the basic physics of how the signals propagate, it won't be able to go through. Of course, it does depend on the material's characteristics as well, but in general, if the signal is trying to go through an obstacle that has thickness larger than its wavelength, then it attenuates significantly. Because of this physical phenomena, we can get the radio waves into our buildings very quickly because they can go through these walls with large wavelengths, but optical beams can't. And they attenuate really fast because of all that. So we have to work with these challenges. In research, there's always some challenges that we have to worry about and we have to solve. And what I'm trying to do with the optical wireless or free space optical communication is to make it available for general purpose communication and improve our basic communication systems that we use for wireless systems. Like I'm hoping and imagining these lights that we use today in the buildings, they will be able to not just illuminate us, but also send bits to our phones, to our mobile devices. But there are lots of challenges, of course, still that needs to be addressed. That's why there's research for it.
When I first came to UCF, I really wanted to do photonics. engineering instead of electrical, but I decided to go with electrical because with electrical you can go into photonics, like kind of how you did, I guess. Yeah.
Yeah.
So what like side do you like more? Like, do you like the photonics side, like the optics and that kind of stuff, or?
I am more in the computer engineering side of it, to be honest. I'm by training as well as my interest. I have to understand the physics of it so that I can make some engineering out of it. But my main engineering focus or research focus is on the computer engineering side. I'm more interested in building systems that use optical wireless. When you say photonics, for example, you have to work very closely with the physical phenomena to do something, to get something reasonable done. I work with more on the computing systems that try to use optical wireless physical resources in order to get something done, if you will. I mean, that's what I focus on. So the short answer to your question, I'm certainly towards on the EE side or the computer engineering side, not in the CREOL side, certainly. That's why my home position is an ECE.
Yeah.
Great. We know that you're an advisor for our IEEE's drone project. What are your thoughts on that, and what do you think about drone delivery?
Well, I hope it becomes real soon. When this comes to my, this question, when the issue of drones come to my, brought up, I immediately think about the smartphones. It may be a weird analogy, but smartphones changed, revolutionized actually our lives, for good or bad. I mean, they're like certainly good, but also there's bad. According to research output, by the way, not just my opinion. But it happened in 2007, right? I mean, we started with this iPhone becoming a real product, and everybody was able to purchase it quickly, and then it immediately started impacting our lives. I think drones are probably going to be one of the next thing that change our lives. I mean, it's very similar to the smartphones revolutionizing our regular life in 2007 and onwards. I think drones are going to do the same. Drone delivery is certainly one of the applications. They're very, that's a cool application, obviously. But there can be many other scary applications too, right? I mean, but eventually being able to fly and doing autonomous work is actually a very interesting combination and will enable who knows what kind of applications. I mean, when smartphones came along, I don't think the inventors of smartphones, just like the invention of the internet, inventors of the internet back in 70s and 80s, just like they didn't understand what the exact implications will be 10 years down the line. Smartphone inventors also didn't have that perspective. I think with the drones, it's the same. It's coming, certainly. That's now clear from a technological point of view and economic point of view as well. I mean, both technology and economic forces seem to align now, that there are enough applications that will drive economy for it. It will come together. But do we know exactly what will happen 10 years down the line in terms of what other kinds of applications will arise? We just don't. That's the fact of it. I mean, we immediately think about drone delivery, which is a great thing. Let's get it done. But who knows what's going to come up with it 10 years from now.
Yeah, that's true. I find it very interesting, that process. And yeah, but as you say, something can happen from here to 10 years on, so we don't know.
Yeah.
I also think drone delivery is pretty interesting. But can you talk a little bit about your advising for the IEEE drone project?
Well, I mean, I'm hoping that it works out well. I mean, we are currently trying to do a drone show for the potentially for the halftime show of some of the games, but it could be for other purposes as well. I'm pretty sure you have seen various videos of doing drone shows during the night most of the time for various games and other kind of entertainment events. We are trying to put together essentially a show like that. They are looking for sponsors, which is going to be a major issue. There are clearly some technical challenges that need to be addressed, but I don't see them to be extremely difficult. I mean, they're engineering work. We will have to get them done. But I think it's crucial that we find some sponsors.
Do you have a big team for it so far?
As far as I know, yes, there's like tens of students are very much interested in it. Yeah.
Oh, collabs. That's exciting. So do you mind telling us a little bit about project management and how you go about it and how you use it for maybe advising or when you were in the industry, stuff like that?
Well, managing, projects these days involve quite a lot of human aspects. We all have our own view on the world, and managing a project does involve making sure that people's views align towards the same goal. In a PhD program, it becomes a bit more challenging because the nature of a PhD is that you focus on an area and sort of like make a deep dive. And the nature of a deep dive is you do it mostly yourself. So I wouldn't say that this is something that you can do in most of the project cases. For example, in the industry, you would certainly work with a team. There's almost nothing left that you can do alone in the industry in terms of engineering work. You will work with several other engineers, meet with them daily or multiple times per week, assess what you're doing, and then advise each other. That's how it is. In my case, I try to bring my lab together every week. I meet with my students every week again, at least once. But there are differences between what happens in the industry projects versus an academic project. Or PhD project. I have to acknowledge that. In terms of PhD, it's meant for doing something deep, while also trying to gain some breadth and in your area in general, trying to understand what others are doing. And in my opinion, a good way of managing a PhD group is to make sure that everybody can talk to each other, not maybe at detail, at depth, but at least can understand each other. I try to do that in my weekly meetings. But again, there has to be some deep dive for each PhD student. So I don't know if this is what you had in mind, but love to have any other questions related to it, because it is since there's a human aspect to it, it is a crucial issue. Your management environment or in project environment in general, it can become a challenge or it can become a big enabler. So
how would you usually organize a project like in your PhD? How did you organize it?
I typically, here's an ideal situation. Let me describe it. Whether or not I can do it all the time is another question. But an ideal situation would be you have a PhD student or two, and then a few master's students and then undergraduate students as part of a team. And then the ideal way of splitting the work would be, in some sense, the more uncertain work should be given to graduate students or the PhD students, and the more certain work should be given to undergraduate students who can just focus on the job, well-defined work and get it done. A lot of the times in the PhD, in the graduate research, we spend time, significant amount of time on defining the problem, what exactly that we want to solve. It may sound weird, but this is how we do research in PhD level. Actually, it's something that I want to emphasize about difference between academia and industry as well, in the sense, in industry, typically, your problem is very well defined. By the time you start as an engineer, you're given a problem that, okay, well, I need a solution for this. And most of your time goes to finding a good solution to it and then doing testing, which is very natural. Most of the time in industry will go for testing, and most of the project effort is going to be for testing. But in academia, when we are organizing a PhD level work, we end up spending quite a bit of time on defining a new problem that is worthy to solve and would be novel, obviously, something that we can publish papers from it, because novelty is crucial. If you're not doing something new and interesting to people, then it's not going to get published. It takes a lot of time to define what it is. To do that, we read a lot. We make a lot of literature reading at the beginning and try to understand what others did. You have to authoritatively be able to say, okay, well, these people have done that, and these people have done that, and this is what I'm doing, you know. And then you have to be able to position what you're doing very carefully with respect to the others. Believe it or not, that takes a lot of time. That in comparison to actually going in and doing the experiment and getting the work done, finally finishing it, in comparison to that, understanding the overall big picture takes a lot of effort and time. So, but in the industry, that's typically not the case. There's already a set up company, and if you are working as an engineer, I mean, there's also the issue of whether or not you want to start a company. When you start a company in industry, you face a similar problem, right? Of, okay, well, there are these companies doing these things, and there are these other companies doing these other things. What is it that I'm going to be doing as a new company? In some sense, you know, there's a resemblance there between starting a PhD research and starting a startup company.
That is very insightful. I did not know all of that went into that. So that's really cool.
So you just told us about some like main difference between academia and industry. Which one do you prefer?
Obviously academia, because but that's my personal choice. Let me just summarize that. I worked, as I said, I worked as an engineer for about a year. Prior to that, I worked as a research intern at Sun Labs, which is a company that doesn't exist anymore. Sun Microsystems, which was a beautiful company. Went bankrupt in the 2001 .com bust. I have to remind that to people. I actually worked in the company as a summer intern in 2001, and then right after that summer, we had this big .com bust. You know, a lot of you guys, youngsters, don't remember that at all. Maybe you were not even born. So that continued for about 5-6 years for the market to recover. After 2007, roughly 2006, maybe, it started recovering. I'm talking about starting to recover. For about 4 or 5 years, there was almost no hiring going on in the market. A lot of big giant companies went bankrupt, and Sun was certainly one of the highly impacted companies, negatively impacted companies. Anyway, so the difference between the academia and industry, and you ask me which one I prefer. I prefer academia because I want to be able to, teach. That's, if you will, that's the key difference among many differences. That's one of the main differences. One of the main differences between academia and industry. In industry, you're not expected to teach. In academia, you have to teach. It's part of your job. Here's the other main difference. I alluded to that a little bit earlier, but another main difference in terms of the work you end up doing, in terms of the research and the actual projects you do in academia versus the industry, other than the teaching difference, of course. In industry, you're again working on hard problems, but very well defined. Most of your time goes to testing. Again, I'm not saying this, testing by itself is a big system, right? It takes a lot of effort to perform a thorough and well-established testing system. That by itself has, if you will, has a science to it. But as an engineer in industry, that's what you're going to do most of your time. Design and problem definition, it's probably going to be 20 to 30% of your time, and 70-80% of your time is going to be doing testing. In academia, when we do projects, it's the other way around. We spend a lot of time in designing and as I said, doing surveys and trying to understand what we can do and finally defining a problem. And doing a sort of like a quick and dirty testing to prove the concept. It's mostly about, okay, we have this idea, right? And we have some solutions to it, and here's a proof of concept that shows that our ideas work for this problem. In academia, that's how it is. But obviously in the industry, the threshold is much higher in terms of reliability and in terms of satisfaction of customers. So naturally, the amount of testing that you have to do is significantly higher. So, but I have to also say, it's a personal choice. I'm not saying that one is better than the other one, or one is a smaller job than the other one. Actually, I've seen during my time in the industry, I've seen super smart people. I would even say almost all of them I've worked with are really, really smart people. And I enjoyed working there, actually. It's just that I still think that, I think for me, being able to do teaching and facing the students is something that I like. So
yeah, it's something like more valuable, I believe.
For me,
yeah.
Again,
yeah.
It's for me. For some others, it may not be, and it doesn't have to be.
Yeah.
All right, here's the big question of the podcast: Mac versus Windows.
Mac, certainly.
Me too.
Mac, yeah, certainly. Well, you can debate about that, but
no debate needed. Toby wants to debate, but not me. I love my MacBook. I love my iPad and my iPhone. I love Mac.
Yeah. Well, let me just say a few things about maybe Apple in general and Mac. Actually, it does resemble quite a bit to Sun. Sun Microsystems in late 90s and early 2000s, as I was saying, if you will, the computers that you would get from Sun were, again, I hope nobody is getting offended by this analogy, but these computers were the Mercedeses of the computers, really. They were like very, very strong, reliable computers. I'm referring to Sun workstations for those who are old enough to remember them. Right now, I think, at least for most of the time, Mac has been there this way. In the recent years, seems like there's I don't know. I've also had some bad experiences with some of the Macs. But am I still like a Mac fan? I guess, yeah, sure. Because they, I find them to be much more reliable. You get less
like viruses,
less attacks, exactly. And then you can rely on the computer more in general. But again, does Sun Microsystems as a business did that survive? No, unfortunately. I'm not saying Mac is or Apple is doing exactly the same. They are doing very differently some of the things. They have changed. But going 10 years ago, they were very closed. I was really worried about their closedness in the sense that they wouldn't allow any other interfaces to work with their systems in, operating systems or the hardware systems. Now they seem to be more open, which is something that is necessary when you look back the history of high tech. Arguably, one of the key reasons why that Sun Microsystems, or again another company that you wouldn't know, SGI, these companies were they were pioneers of a lot of the technology back then, and Believe it or not, we are still using some of what they have done. But they went bankrupt because of their too closed business model. And they wouldn't allow, for example, you wouldn't be able to hook a Sun workstation with another keyboard. You had to use their own keyboard. Stuff like that, essentially, being too monolithic and too closed. Certainly, you can make a lot of optimizations that way when you're designing everything yourself, which obviously is the one reason why they're trying to do it that way. But of course, in terms of a business, when there's the competition out there, and you have to be able to work with others in some way and collaborate with others in order to get things done and make sure that you survive in the long run.
Yeah, I remember for one of my classes, I needed to have Windows, but I had a Mac, and I was like, oh my God, I have to download Windows onto my Mac now, which makes the computer very hot. So
That's a heresy.
yeah, but that's okay. It's good now. I don't have to use Windows again unless I'm in the lab. So we kind of want to talk about like soft skills versus hard technical skills. If you want to give any input on those.
Well, I mean, the thing that comes to my mind, I haven't really thought about that one. The thing that comes to my mind is being able to work with others. Is crucial in our environment. There's no place like you have your own cubicle and do your own work and nobody else. You don't have to deal with nobody else. I mean, the human factor is part of what we do. In that sense, I think all of us, particularly as engineering majors, need to have more proactive approach, in my opinion, on this issue, where statistics are showing that most of us are introverts, and we have difficulty talking to others, and again, it's just the way things are growing that way. And I think it's crucial to be proactive and develop human skills and social skills as part of our programs. Now, how to do that as a program is a big question. I mean, there are, of course, courses that we have. We try to emphasize project work, teamwork. I'm sure you have seen cases where you go into a project with a team and then you regret it. I'm sure you have had that. But trust me, this is part of life. It is a learning experience that you are going through. I mean, I've seen from my own kids actually that they would tell me, I hate this project because I have to work with these people and so on. I mean, it just happens. I've heard a lot from various students, including my own kids, as I said. But it's part of the training, and being able to work with others in the long run is going to make a huge difference for your careers. Yeah. Let me also say that this is now how to solve this issue. I mean, how to make it like for example, what is the best way of organizing a team project in a course? I have to say, I haven't found it the best yet. I mean, I'm still searching, because you always have these type of issues between the students and in a team. One student does more and then the other student does less.
Yep.
And then, you get all kinds of complaints and so on. Trust me, again, do your best and try to be as proactive as you can to handle these type of human factors in the engineering work you're doing.
Yeah, it's definitely difficult trying to make friends in classes, but that's why we have clubs like IEEE.
Oh, yeah.
We have workshops that help develop your skills. We love it here.
Absolutely. I mean, I guess if you want me to say, I think it's obvious, but you should certainly, by being proactive, this is what I mean. I mean, you should be involved in something other than just your own paper, just on your own text or whatever. I mean, do something more, do something with people.
Yeah, and I also think that COVID was something that like make us realize that as students. I know that while we were in COVID, like most of the people were just living on their own like bubble and online classes and all of that. We don't have to interact a lot with people. But after COVID happened, it just like, oh, we're like free again because we can go to campus, meet new people. So yeah, I completely agree. And with you, Julia, that you say that sometimes it's really difficult to make friends in classes because most of the people just go take the class and then they leave. And if we
Right.
don't have like group projects, then we don't have any way of interacting with people than other just like organizations and that. So I completely agree. And talking about students, is there like any advice that you would like to give to our
Professors always give advice. I don't want to go into like too philosophical stuff, but maybe the thing that comes to my mind here is try to develop skills that will last long. I mean that's being focusing on specific technologies is not really what is meant for, at least in my opinion, for a bachelor's degree in engineering or sciences. What will make the market is great right now, right? I mean, it's doing great. I gave you the example of the time when it may not be great in 2001. You guys, thankfully, are not remembering it. But it can happen, or the way things are going, it will most likely happen. I mean, in the sense, again, it's just the nature of it. It's a cycle. Well, who survives through these going down cycles are the people who are, who have developed both problem-solving skills that last longer than specific technologies, as well as who have human skills. I mean, try to develop them. Certainly, you gotta develop some know-how on specific technology, but what matters eventually in the long run is your solid problem-solving skills, which, does not immediately happen. You have to work on many problems, and then you naturally develop some skills that you don't even realize it, but it happens in you. And then, that develop that maturity. Try to do more work. Obviously, is one way of doing that. Trying and solving different problems, not just one type of problem over and over again, is another way that you can improve that. And as I mentioned already, the human skills is crucial. Try to work with others, even though it will sometimes hurt you. It will try your patience. Those are the skills, again, that will make you survive in the long run. Not survive, but thrive, actually. I mean, survive is the wrong word. I apologize. I'm not trying to I hope this doesn't come across negatively. I'm just saying, we are currently in a great time, right? I mean, the market is doing great, both in this type of a market, as well as in a market where the cycle is in the down phase. If you want to thrive, right? I mean, you need these skills. So try to develop them, even though it helps, even though it hurts your patience. I mean, touches your patience sometimes.
Yeah, I believe teamwork is the future also. Like you graduate from college and then you go either to industry or academia and you have to work with people and interact with others. So yeah, teamwork is definitely one thing that we need to develop as students.
Teamwork makes the dream work. That was actually my middle school motto. That's not a lie. Well, thank you so much for coming on to our podcast today. We really appreciate it.
Thank you so much for having me, and thank you for doing this great work. And keep it up, please.
Thank you.
Thank you.
Mic drop.